Good evening. One more time, folks. Good evening. Thank you. Welcome to the Shoals Marine Laboratory's weekly marine science seminar. I'm Sarah Morris, the John M. Kingsbury Director of the Shoals Marine Lab, and I want to thank you for joining us for tonight's seminar, which is the fifth in our 2024 season. Our seminars are affectionately called Rock Talks, in part because back in the early days of the lab, seminars and classroom lectures would take place in the intertidal on the rocks. Although we now meet in the commons, these weekly seminars provide a wonderful opportunity for our island community to come together and learn about a range of topics related to marine science and to our environment. For those of you joining us online who may be new to our lab community, the Shoals Marine Lab is the oldest and largest marine lab in the country that is focused on undergraduate education, both in terms of coursework and in research. The lab is operated jointly by the University of New Hampshire and Cornell University. In addition to our guests joining us online this evening, we have 3 courses on Appledore: Anatomy and Function of Marine Vertebrates, Ecology of the Marine Environment, and Marine Environmental Science. We also have our summer undergraduate research group, affectionately known as SURGES, who are involved in summer-long research projects. Now you can go. We're excited to have everyone both in person and online joining us tonight for this seminar. The format for tonight's seminar will be a 45-minute talk followed by 15 minutes of Q&A. For our friends online, please use the Q&A button at the bottom of your Zoom screen. We will read your online questions out loud for the entire audience. For those of you in the commons, I'll be passing around a microphone for questions from you on the island so that everyone can hear. This evening's speaker is Dr. Diane Foster, Director of the School of Marine Sciences and Ocean Engineering, and a Professor of Mechanical and Ocean Engineering at the University of New Hampshire. Dr. Foster holds a BS in Mechanical Engineering from the University of Massachusetts Amherst, an MS in Mechanical Engineering from the University of Maine, and PhDs in Civil Engineering and Ocean Engineering from Oregon State University. No pressure for the rest of us. She's a leader in her field of coastal sediment transport, with a research portfolio that includes support from the National Science Foundation, Department of Defense, National Oceanic and Atmospheric Administration, U.S. Economic Development Administration, and more recently, the Department of Energy. Her scientific call to action has centered on resolving the dynamics between fluid sediment or fluid sediment structure interactions in coastal environments through a mixture of fundamental theory and novel field and laboratory observations. As the former director of UNH's Chase Ocean Engineering Laboratory, she led UNH's efforts to establish an undergraduate ocean engineering program and expand its ocean engineering research capacity with a major renovation and building expansion. And if you haven't seen the Chase Lab, it is amazing. You need to go visit. Since coming to the UNH Marine School, she has generated funds to launch a new department, a new Center for Sustainable Seafood Systems, and supported the launch of a new Department of Energy Atlantic Marine Energy Center. She serves on the executive committee of the U.S. Coastal Research Program and New Hampshire's Offshore Wind Commission. She believes that addressing our increasingly complex societal problems impacted by our oceans will require a firm commitment to interdisciplinarity and stakeholder engagement. Diane has a long history of supporting students and fostering outstanding education. She's received the Graduate Faculty Mentor Award in UNH's College of Engineering and Physical Sciences in recognition of her support for both education and research. As an engineer, she believes strongly in providing the women in her life a toolkit, literally, because she believes every woman needs to be able to fix things. She is one of the Shoals Marine Lab's strongest advocates and supporters, recognizing and fostering the unique role that Shoals plays in undergraduate education, mentoring, research, and sustainability. She's helped us secure numerous gifts, grants, and scholarship support. We are truly lucky to have her in our corner. It is my honor to introduce my colleague, my friend, and officially my boss, Dr. Diane Foster, who will present her talk, The Rolling Stones, Rock Band, or Grains on a Beach. Please join me in welcoming Dr. Foster. Thanks.
For the record, I don't recognize most of that. Also, I only have one PhD. There's an HR glitch at UNH and it has me listed as 2. So I'm ordinary, but happy about that. So I'm an engineer and I do a lot with differential equations and electronics. And some people are really into that and some people aren't that into it. And so as I was thinking of giving a talk, I thought about what my 21 and 25-year-old would say. And we're going to do, has anybody heard of this old game show called Let's Make a Deal? Yeah, so we're going to do this thing where I'm going to show you a couple of topics and then you're going to tell me what you want to hear about. So I'm going to show a couple of slides on several different things and then you're going to say, this is the one I want, and we're going to go with the most votes, okay? And a lot of what I do is, so the Rolling Stones really is characteristics of what my students and I really work on, and I consider it to be a real honor. What do we recognize when we look at that video? Big waves, right? Lots of foam. Offshore wind. Offshore wind. Put a pin in that, and I'd like you to remember that in just a little bit. So I'm just going to have one slide on sort of the UNH marine enterprise, since a lot of when I'm actually talking, it's about sort of the broader enterprise. And I really like to think about calls to action. What are the things that make me get up in the morning? What are the things that make me really excited to put on a wetsuit? What are the things that sort of make me want to what are the things that speak to me? And all of you can probably tell me what your calls to action are. And if I look at our marine enterprise, and just to give you an idea, UNH is now 6th in the nation in federal research spending on ocean sciences, which is pretty impressive and a real point of pride. We have excellence in sustainable seafood systems and coastal resiliency, ocean renewable energy, and then also in marine environmental sensing. How do we detect what's happening in the Gulf of Maine? How is it changing? How might it change? What information can we glean from satellites? What information can we glean from water particles? And also Arctic studies. We actually have a really big cold climate and Arctic studies group. And finally, ocean mapping. UNH is without question the world leader in coastal and ocean mapping. And I think the thing that makes us so successful, because really, if you divide us by miles of coastline, we are punching way above our belt, right? 19 miles of coastline in New Hampshire. So if you divided by everybody's miles of coastline, we're doing really well. I think it's this premise of engaged scholarship. We listen to the people we work with, we try and think about problems together, and we come back and work with them regularly. And I think that is really what defines UNH in my mind. So today I'm going to talk about coastal resiliency. And I'm going to talk about it along our 19 miles of shoreline here in New Hampshire. This purple and orange map that you see is actually the map that has been put together by UNH's Coastal and Ocean Mapping Center, and it's a multi-beam sonar map. So we can actually resolve the seafloor geometry to a really sub-meter scale when we're ready to do that. You're going to hear me talk about things like Wallace Sands Beach and Rye. That's just south of Portsmouth. We can probably see it almost. We can probably see it from here. I'll talk about Straws Point and Rye. We are here in case any of you are wondering. And then down, the thing that looks like a lad's lamp, that's going to be Hampton Seabrook Estuary. And you're going to choose which one of those things that you would like to hear more about in just a little bit. Okay, so first, I'm going to talk about door number 1. Thin layer deposition in Hampton Seabrook Estuary. This is a drone photo of Hampton Seabrook Estuary. One of the things you notice is we see these salt marshes that often have trenches that were done by farmers centuries ago. And another thing you see is that there's a couple of smallish spits that have a lot of population on them, right? You can see houses behind me. The one to the north is Hampton, the one to the south is Seabrook, and the inlet is then the Hampton Seabrook Inlet that leads to Hampton Seabrook Estuary. This gets really interesting because 70% of the tax base in Hampton, Seabrook, and Hampton Falls actually lives on that spit, 70% of the tax base. So as sea level continues to rise, as we see more extreme events, this is going to affect the way they live. It's going to affect their schools and their fire stations. So we can sort of think about that, and we can think about, can we do anything about that? You know, and I am an engineer, so like engineers like to do things regardless of whether we should sometimes. But so once again, one of the option one is Hampton Seabrook Estuary. This photo is of Hobson Avenue. Hobson Avenue has a number of young families that live on it. Notice there's no wind in that photo, right? Water's calm. This is what looks like a typical high tide. You can imagine that that water level is fairly close to those houses. There are young families. Once a month, they typically can't park their car at their house. They have to park it at the police station and carry their kids and groceries back to their house. Sometimes, though, when you have a storm and you start to see larger storm surge, you see something that looks like this. Their basements are flooding, sometimes their houses are flooding, and this is happening at an increased rate. Okay, now I want to get back to ecosystem stuff. So notice that what we know about salt marshes is they're really important for the ecosystem. They're also really important for the built environment. Now, does anybody know, how do we protect shoreline down in Florida? What's a really common strategy, natural system for protecting shorelines and homes and communities in Florida or warm climates? Mangroves, right? Yeah. Do we see any mangroves in New Hampshire? No, we have a cold climate. And I think we're only beginning to address how that cold climate and what sorts of things we need to do in order to protect our coastal communities and ecosystems might look like as we move forward. Okay, so David Burdick, a colleague of ours, has then been measuring for the past 10 plus years. He measures the elevation of the salt marsh every year. And I'm going to show you this figure again, but this is just my teaser figure. Remember, we're on door number 1. And what this figure shows is that over a 10-year period, so that's from 2012 to 2024, and he measures it at multiple different locations. And notice that what that says is it's trending upward at a pretty linear basis, right? It's trending upward at about a little over 2.2 millimeters a year. So that means it's what? 2 centimeters over a 10-year period. That's almost an inch that the salt marsh is growing. That should be good because the higher the salt marsh is, the more it then can protect our coastal communities from flooding. Well, unfortunately, sea level is rising locally here at 4 millimeters a year. So that means that our salt marshes are actually losing relative to sea level rise. Well, what does that mean? It means we're drowning our marshes. It means low marsh is now becoming a mud flat or might become a mud flat. High marsh becomes low marsh. Loss of ecosystem services provided by the marsh and a reduction in coastal resiliency. I will also point out that at the backside there is Seabrook Nuclear Power Plant. So this matters, right? So door number 1, we stay in Hampton. We're going to come back to Hampton Seabrook. And we're going to say, I want to learn more about Hampton Seabrook. Door number 2, we're also going to talk about, and all of these things I'm talking about involve sediment, right? Whether it's little tiny sand grains, whether it's larger sand grains, whether it's how we deposit sand. So they all involve sediment, which is my jam. So door number 2 involves this principle of overwash. Has anybody heard of overwash? Well, maybe in your coastal regions, one of the things that you end up with this big storm, and then all of a sudden there's a whole bunch of sand on the roads, and the plows have to come and they have to plow the sand out of the road, right? And we know the number of days a year that we are not able to travel on roads because of coastal flooding is going up substantially. And overwash, we typically, from an ecologist, think that overwash looks something like this little cartoon that I've shown. So water gets pumped up from storm surge, right? So essentially winds are blowing across the ocean. There's pressure variations. It pushes water up and then you get large waves. waves now are able to break a little closer to shore because the water level is higher. You keep pushing it and eventually it breaks through. And then you create something called an overwash fan. Now, if I'm thinking about this from a transportation perspective, I'm probably thinking this is a bad idea. And I'll show you a photo of that. What we know, though, is that in order for marshes to grow, they have to have regular supply of sediment and salt water. So in order for these marsh plants to continue to grow, they somehow have to get sediment. If we start cutting that off, it means there are saltwater marshes may become freshwater marshes, and they are not going to keep up with sea level rise. So one of the takeaways here is that sometimes extreme events are good, depending on your perspective. And we have several places along the New Hampshire coast where we have these overwash fans. And they look like this thing, and it looks like literally sand has gone up over the dune and down the back of it. So you can see these overwash fans. And we have clever ways of measuring them. Anybody know what an RFID tag is? Right? The thing that beeps when you leave the clothing store if they end up not taking the tag out. We actually put them in rocks, and then we measure what happens to the rocks and how they move up and over the beach so that we can actually determine the amount of shoreward transport of sediment. Now, often when we think of overwash, we actually think about this, right? Where sand is washed on the beach. One of the issues we have locally is that we have Route 1 that goes right along the beach, and we often have salt marshes on the other side of it, which means that when we're prohibiting sediment from moving across that road during these extreme events, we're likely starving our marsh. Now, if you want to tackle a problem like this, you need a nearshore hydrodynamicist, you need somebody that understands dunes and sediment transport, and you need a salt marsh ecologist. And you're transporting sediment across all of this space. So it's a fairly complicated scientific problem. Okay, that's door number 2. So you're gonna all vote on which one you want to hear more about. Door number 3 is our dynamic beaches. This is a photo of Wallace Sands. We do a lot of field work at Wallace Sands. We typically do field work not when people are surfing and when the weather is really terrible and in the middle of the winter. And one of the things we know about beaches is that this is just a cartoon that I found on the web of a typical beach profile. And notice that we have waves on the offshore. They get to shallower water. They conserve energy flux. They eventually break. When they break, they create a lot of turbulence, right? And then they get to the shoreline. And then if you go a little bit up the beach, sometimes you have a berm and sometimes you have a dune. But then when you get these large wave events, waves start breaking farther offshore. Sometimes that's also associated with storm surge and setup. So sometimes you also get waves breaking offshore and you end up with this raise in sea level rise. So you end up then typically your beaches erode. Are people familiar? What typically happens to our beaches in the winter? Anybody go to the beach in the winter? We often loss of sand, right? So they do sometimes freeze, actually, and that's a really interesting problem, but I didn't include that in one of the door options. But we do have this loss of sand, right? And so what happens is our beaches typically go away. Now, what we know is that often that sediment just goes offshore a little bit, and it ends up building sandbars farther offshore. Sandbars are really good, and it's actually if one subscribed to the Gaia hypothesis, one could say it's Mother Nature's way of protecting our beaches because it forces waves to break farther offshore. The farther offshore they break, the more they dissipate their energy. So it's a way of sort of protecting beaches. And then typically in like spring climates and over the summer, our beach then rebuilds and it recovers. And that's generally the way we think the world works, right? And people worry about their beaches going away in the winter, and then they suddenly will rebuild. Sometimes it doesn't, though. And so one of those examples is that tropical storm Lee. And I showed you that short video with the offshore directed wind. And a grad student that I have the fortune of working with, Melissa Mary, has actually been measuring beach profiles every single month at Wallace Sands. And she saw that even though we had this really big storm, we ended up with actually the beach rebuilding as a response of this extreme event. And so this is a typical beach profile, the biggest bump here, and this is just going to go from every month, August, September, October. And you're going to see it jump around. And notice from September and October, the beach got higher. So that meant we had a really big storm and the beach raised, and it raised by 50 centimeters. So we ended up with that much sediment added to the beach. Likely contributing, a contributing factor was likely that offshore wind. Also, we didn't have really strong currents. One of the things we can do as physicists is we can predict when a beach will erode really, really well. You end up with waves coming in an angle, they end up breaking, you end up with big currents, and they push sand all over the place. We cannot, we don't know as well, we don't know as much about how to actually build the beach back up, right? So we don't have quite, and yet Melissa has a theory on how that's done. And that is going to be door number 3. And I want to comment. So between August and September of last year, the beach went from the red line with the bump at the top to the flattish line. And it looked like we were starting to do this fall thing where you get big waves, you get sand that's from the top of the beach and it goes offshore and it fills in offshore. So it's looking like the stuff we know. Then October, she went back for her next survey. And now we gained almost 50 centimeters of sand almost everywhere. That came from the offshore. Another thing that happened in the Northeast in January is we had these horrific storms in January, and some of you may remember it. So Melissa kept going and she went out and did her December survey. Now we've lost all that sediment that we had acquired. And remember, in a lot of places, it's over 1 meter of sand that we've lost. So we've lost this much sand from the beach. And what she found is that between December and January, once again, the beach suddenly rebuilt. And that was during that really large event, that the January events that caused such destruction locally. Okay, so right now is our pivot point. And I have talks for any of these 3 topics, and you get to choose. So rather than cramming them all in, I'm going to give us a chance. And I hope that for the next bit, you take the time, raise your hand, ask questions. The goal is to find something interesting that you may want to think about in the future or even now. So door number 1 is Hampton Seabrook Estuary, right? That's our salt marsh. Door number 2 is Dune Overwash at Straws Point. And door number 3 is our changing beaches at Wallace Sands. All right, so people that would like door number 1, right? That's Hampton Seabrook. That's the salt marsh behind in the estuary. Can you raise your hand? Okay. Door number 2 is the Overwash. Okay. And door number 3. All right. I think 1 has it. And I think 1 has it, right? Are we all in agreement with that? All right. So 1 has it. So we're going to go to Hampton Seabrook at this point. The people that have done all the really great work here are people like Tom Littman and Greg Moore. Greg Moore is a regular instructor out here. Tracy Mandel, they're all faculty at UNH, and Mike Pallas, David Burdick, Jengwen Choi, and Elijah Russo. And they come, notice where they come from. They're engineers and are scientists and biologists and natural resource. So these kinds of problems are tricky problems, and they need people with deep disciplinary understanding to work together. And often we end up learning a little bit. Okay, I think you've seen this photo already, but I just want to remind us we're in Hampton Seabrook Estuary, right? This is a Google Earth image of Hampton Seabrook Estuary. Can you see why I think it looks a little like Aladdin's lantern? Notice that we know that it's probably, a sediment person would look at this and say, it's probably pretty flat estuary, because you notice how all the tributaries are sort of snaking and curling in. That tells us something about it. Notice you see some white patches. That's probably sediment. There's some mud flats there. We know it has this extensive salt marsh system. We've already learned it's losing about 1.5 millimeters every year relative to sea level rise. So one of the things we know is that things are going to be changing, right? We know it's very important to both our region and just the ecosystem in general. So we have a group of people that are starting to ask the question, well, what do we do about it? Do we basically just accept that this is going to happen? Maybe we do. Maybe what that does is it informs adaptation decisions. We as a community need to make decisions of whether or not we're going to move our homes and abandon. But are there things that we can better understand that may help us make a decision? And there are a couple of things that UNH folks are starting to think about. And one is a riff on a Dutch program. Has anybody heard of the sand engine in the Netherlands? It's massive nourishment projects. And I did some field work there in the North Sea several years ago. Another is the mud motor. And the Dutch are pretty clever, right? More than half of their country is below sea level rise. So they have to spend a lot of time thinking about water and land and the intersection. And the Dutch argued that, gee, well, I wonder if we could use sediment transport to our advantage to protect our estuarine systems. One of the things they did is they said, well, maybe right now we dredge these inlets to allow ships to come in and out. Maybe rather than dredging the sediment and taking it offshore, we can just kind of mix it up a little bit on an incoming tide. And then that incoming tide will then pull the sediment in. Because we know that if we take a dump truck and dump it on a salt marsh, our plants are going to die, right? So we can handle a certain amount of sand, but we can't handle too much. That's why we call this thin layer deposition. We want regular supply of sediment. So we don't know that this is going to work, but what we know is that we can't even understand how plants are actually going to trap sediment unless we start sort of understanding the salt marsh response to water, the hydrodynamics in the estuary, and how plants actually trap sediment. So this is really the beginning phase of a sort of multi-year project. Okay, so this is Hampton Seabrook Estuary. And then the next thing, Greg Moore thinks, well, gee, I can actually get this much sand there. I can get a bunch of sand there if I look at a couple of really large extreme events where there's this thing called ice rafting, just like what it sounds like. And we're going to talk about that again. So I'm going to talk about both of those things. And I am not going to come up with a conclusion. As an engineer, that's always hard for me, but I'm not going to come up with a conclusion. Basically, these are things for us to think about and that we can better understand the system. So if you're going to try and get a hydrodynamic model running in this really complicated system, right, with all these tributaries and with tidal flows coming in and out, you need to understand a lot about dispersion in these water depths that are varying substantially over a tide. And so Mike Pallas and Frankie Sullivan and Tom Littman have been using some rhodamine dye. And they basically then use hyperspectral cameras to try and measure the mixing so that they can then calibrate the model, because we're not just going to start dumping sediment in, right? We're going to actually try and predict, and we need to know that we understand what's happening. And then they chase this dye around on boats. And then the other thing that they do is we are working with a startup company of a recent UNH grad on GPS drifters. So imagine having a GPS antenna, but now it's in something that floats and you know where it is really well, and then you can then track it. So then they put a bunch of these things in, and then they're running around on boats tracking the drifters. And when they do that, they can actually track the drifters up in and around the estuary. So they have quite a bit of confidence now that the model is behaving the way they think it should. So then they started putting sediment particles in, and this simulation is going to keep going, and you're going to notice that they're putting them in right at the incoming tide, just on the inside of the inlet. This is now it's coming out. So they're putting particles in that are not quite either neutrally buoyant or not quite neutrally buoyant. I think they do both simulations. And you can imagine then that they can then see, so you could then quantify how much sediment do you need to have in the water in the inlet in order to get the kind of deposition you need. Do you need to do it every day? Do you need to do it every Tuesday? We're also going to have to think about how is this going to affect any of the shell fisheries, right? Because now you're going to have more sediment in the water column. So this is one of these kind of tricky problems. But they've now, because they've done the work calibrating the model, they can then start asking questions of it. What size sediment do I need to use? Do I need to use clays? Do I need to use coarse grained sediment? What is that going to look like? And they're coupling that with some detailed studies on the Seabrook side of things. So this is Elijah Rousseau, who's working with Tracy Mendel, Tom Littman, and myself, and deploying a series of instruments in Hampton. And notice that this, I think, happens to be high marsh, but there's also low marsh vegetation also. So what can we learn? Can we actually measure the settling of particles? Can we measure the dissipation of energy? Can we measure the amount of turbulence? Because that's one of the things we're going to need to do. This is a nice cartoon of that. So we've deployed a bunch of our instruments, and then we sampled from high tide to low tide, and we do that over a period of weeks. So we get a very good understanding of what's happening with the flow field. And we also measure the sediment properties because we need to know what sediment is there, and then we need to go back and check to see what sediment may be coming. But Tracy's also really clever, and she actually does this in the laboratory also. And this is fake grass, right? So this is fake seagrass, and she has specifically built a flume. And I don't know if you noticed, did you notice that it was sort of rippling a little? Does anybody know what that's called? It's called Manami. Sometimes you see it in the in cornfields, and you see it, or grass fields, and you'll actually see it sort of rippling. And this is sort of the fluid instability in response to a flexible boundary. So Tracy and Elijah are also trying to do this in the laboratory. Okay, so that's one of the things we're doing. And I'm checking on. Okay, great. Another thing that Tracy is doing, another thing that Greg is doing is he said, okay, this is all well and good and it has promise, but I think there's another way of actually getting sediment, thin layer deposition into the marsh. And he did this because he was actually starting to study it. And one of the things he did was he identified and found this thing he called ice rafting. So imagine that it's in the middle of the winter, and imagine you're in a cold climate, right? We're in a cold climate, we can't grow mangroves. And you end up with these big blocks of ice that end up sitting in mud fields. But imagine you then have a really extreme storm event that basically comes in, the storm event comes in, remember storm surge, right? So it picks everything up off the ground, transports it in, and then all of a sudden the water falls, the ice is heavy, right? Because it's in the air, falls like a brick. Any of the sediment that's trapped at the bottom of that actually goes in with it. So what Greg found was that he found a couple of things. One is that people have known about these things called ice rafting for many years, but they did not have any idea of the magnitude of the ice raft. So this is examples of these sort of chunks of ice that basically come in and then get moved over the sediment layer. Okay, what he said was that in two extreme events, and it was a very peculiar winter, and we've got a lot of peculiar winters these days, where we had these big storms that were enough to break loose these ice. In 2 to 3 extreme events, he saw the equivalent of 10 years of that deposition. Remember that 2.18 millimeters per year? So that 20 millimeters a year or 2 centimeters a year. He was seeing not quite an inch of sediment deposition in the marsh because of those 2 ice rafting events. So I guess I say this because I like to ask the question, you know, we hear so much about extreme events and how extreme events are really bad. And I think that they can be really detrimental to what I'll call the built environment and gray infrastructure. But our ecosystem often has benefited from extreme events. So it's really important for us to ask, well, can extreme events actually help us? And we think the answer to that is yes. Okay, so we're thinking that this could be a mechanism for colder climate thin layer deposition. Another thing that Greg offered for this sort of section of the talk is we typically think about an upper circle, sea level rise, prolonged flooding, marsh, and you end up with marshes collapse. I think that says collapse. I can't read this font on here. Marsh collapse, coastal squeeze, and then you end up with losing your marsh. So your your high marsh becomes low marsh, your low marsh becomes mud flats. That's really negative to the ecosystem. But if you can come up with a strategy for successfully thin layer deposition, and remember, we're talking, you know, many millimeters a year. And I think Greg has found that you can deposit up to maybe as much as 10 inches, although I want to double check that number here, before you actually drown the plants. And what he's found is that the actual plants actually do quite well with that. So you can end up, if you revegetate, you trap more sediment. And if you trap more sediment, then you end up with an elevation increase. And then he also has found that it helps the root biomass in this system. And then you end up with increasing your marsh resilience. Yeah, and so he seems to think that additions of less than 10 centimeters are possible in order for the roots to continue and the plants to continue to be healthy. So are natural sediment events on the rise? Too soon to tell, but we think the answer may be yes, particularly as it gets a little warmer. And we saw several of these in New Hampshire, northern Massachusetts. And I guess the next question is, could we use a mud motor for thin layer deposition? Too soon to tell, and there's a lot of implications of messing with something like that, but we do think it's a really interesting question to ask. Can we be more strategic in the way in which we are adjusting and interacting with nature? Okay, and I think I'm still okay on time, right? So rather than getting into the beach change one, although I'm happy to do, I'm going to go just to the second one, but specifically the overwashing one. So I think I mentioned we have several overwashes. We have overwash fans, and we take this multidisciplinary approach with all of these topics that you're talking about. It's not just one type of a scientist or an engineer that's doing this. And this is one of the overwash sites that we really like working on, and it's called Straws Point, New Hampshire. And you'll see that we end up with these natural overwash fans. I'll note that this is not false colored, because when we're going to go out and do these studies, we have to go out in the extreme event. So we deploy 3 days before the event. We think, hey, an event might come. We sort of storm chase, go deploy our instruments, and then we don't go anywhere near it while the event is here, right? So then we leave it alone, and then we come back and we try and find things. And we did this through a variety of different ways. And here's another view of the study site. And what we found is that during this particular event that I'm going to talk about, what we saw is that we saw an extent and an increase. And David Burdick and his team are actually going out and they're sampling and they're taking sediment samples. So they're figuring out what grains were transported. We know that big grains are harder to transport. They don't go as far. The finer grains a little farther, and the finer grains go even farther into the marsh. So one of the ways we can determine the extent and magnitude of an overwash event is by looking at the resulting grain size. And we do that over a whole grid system. But another thing David did was he said, well, I really want to know where the grains are coming from. And I want to know where on the beach the grains are coming from. So we took these RFID tags. They're small, less than the size of my finger. Drilled a bunch of holes and a bunch of cobbles. Injected the RFID tags in, plugged them up, deployed them on the beach in a variety of different places. We got almost all of them back, and then actually tracked them and said, okay, in this one event, what happened? And so this next figure shows us that. So this is an overlook of the beach. The reason it looks like it's false colored is because it was January and snowy, and all the plants have gone dormant. That's why they're brown. The white is either sediment or it's beach. And any of the white circles are the starting points of those cobbles. We're going to call them smart cobbles, right? The smart cobbles, and the blue points are the end points. And we're really fortunate to have got this, because you never actually know where a breakthrough is going to happen. You don't know which part of the dune you're going to have the breakthrough. And what we saw is that all of these cobbles are going, remember, it's pretty steep here. So the cobbles are actually going up the beach, and then they're landing, and then they're often going over the beach. We also deployed a bunch of other sensors. So this is my crowd. Melissa, Mary, Spencer, Marcourt, Savannah DeVoe, and somebody mentioned Maggie Enderly. Who said they know Maggie Enderly? Talked with somebody today that knows Maggie Enderly. We go out and we deploy instruments in the water. Once again, we don't do this during the storm. We do it prior to the storm. And you're going to see that sometimes you see those that looks like a sand anchor, and that looks like our pressure stick that Melissa designed. And so we actually deploy, and then we can actually look and then monitor the water. So we have these pressure sensors, and we know when the water comes, we know where it's coming, and we know the magnitude of the water. And we also get some information about the atmospheric pressure. And then we go and we do these pre and post surveys, and we get to find out where the sand came from and how the beach changed by doing so. Okay, the last thing that I would like to show us, I'd like to show you is that I think that looks at it from a hydrodynamic perspective. It looks at it from the plant perspective, but there's this whole interaction with fluid and flow and plants that's really important. And we don't understand enough about it in cold climates. We know a lot about mangroves, right? Mangroves are really awesome in the South. They have really deep roots. They protect the shoreline really well. We don't know enough about it in cold climates. And we know that plants change. Remember, I showed that photo where all the plants were brown, right? We know that their resistance to flooding is going to be different in that time. Well, we think the resistance to flooding at that time is going to be different than it is in the spring or the summer. So Tracy Mandel, who and working with an undergrad student at UNH, actually did this study where she said, well, I wonder if I can use principles from mechanical engineering to tell us something about fluid resistance. So she thought, an engineer would say, well, what you really need to do is measure the modulus of elasticity, right? Zach's probably done this. He's probably done a lab on this many years ago. He has a mechanical engineering degree. And so what they did was they actually then collected a bunch of plant stems. So they went out and they collected a bunch of plant stems. They took them back to the mechanical engineering laboratory, and then they measured them, and they measured the modulus of elasticity. Does it look familiar at all, Zach? Maybe? It's been a while. But then they measure the amount of bending that any stem can handle, right? So they're measuring the amount of bending that a stem can handle. And what they found is that the modulus of elasticity, so how flexible these stems are, change in season, right? So this says that they're very stiff in August, and then in October and December, they are less stiff. And they did that up and down the coast with a number of different studies, but it's statistically significant. So now remember the model that Tom Lippman had worked on, right, in Hampton Seabrook. You can imagine having to change the parameters for how flooding occurs. So we're trying to sort of come at these problems involving sediment and waves and the ocean and sediment and plants from a whole perspective. So I guess I would say, can overwash strengthen our salt marshes? The answer is definitely yes. We often have a built environment that prohibits that from happening, and there are consequences to that, but we have made decisions about that. Okay, now I'm going to jump to the end. So this is some work we've done really close to here, which is in Fort Foster, and that's another deployment that we were doing, and we were just horsing around. But the question is, can extreme events build resiliency of our coastal ecosystems and beaches? And I would say yes. We still don't know quite how to do it, but we're getting there. And I think with that, I will say thank you. I'm happy to answer any questions.
I'm going to start with a question from our internet audience. Easton writes, there are lots of positives, but could you talk about any challenges that come up when an engineer is working with biologists?
Oh, so many jargon. And I will say, so I am like an engineer. Like the fact that biologists don't always conserve mass really blows my mind. You grow things, and I'm accustomed to whatever goes in has to come out, and that is not necessarily the case, or not necessarily the case. So I think jargon is one. We use different tools. We often use different timescales. my PhD data was 256 seconds long. 256 seconds long was my record. And it was considered an okay thesis. But biologists, it takes sometimes decades for you to understand the system. So I also think we have really interesting questions associated with scale, whether that's length scale or time scale, but we have to keep at it and we have to keep doing it. And I will say Easton White is what we characterize as a quantitative biologist. So he's somebody that often speaks sort of some of the same languages. He uses differential equations in his work and he does a lot of the same things. And I think the more we have those kind of interactions, we can tackle what we call convergence problems, where not only are we addressing the tricky problem, but we're strengthening any of the disciplines. Because frankly, the mechanical engineering, fluid mechanics doesn't touch the complexity of a lot of the stuff that we've been doing. Right? Because our boundary layers are unsteady, because we have slip conditions, our beds are moving. Those are all really complicated problems. So I think it really helps us if we can stay with it. Thanks.
Questions in the room?
This isn't really too much of a question, but earlier you mentioned that the freezing of the shores is an issue that you couldn't get into with the talk. Is it I was just kind of more interested about that. So
yeah. So one of the reasons we developed this thing called a pressure stick is we wanted to measure the pressure distribution within the bed. And partially we were thinking we'd really like to do that in cold climates because we know that there are issues associated with decreasing permafrost in Arctic environments, and they're seeing more days of ice out and they're seeing more substantial coastal erosion. And what we found was that often in New England, we may have groundwater that's just about freezing, right? So the ocean is not frozen, right? But we may be freezing stuff down below. And it seems what we think happens, at least in that limited study, is it looked like it actually stabilized the bed, which is a little bit counter to what we were thinking. And there's a lot more work that we have to do with this, but we see that it deviates from our governing equations more substantially when we're in this very cold environment. I also have to say, though, that before I am able to say that conclusively, I have to understand what my sensor does in freezing environments, because I use diaphragm-based 3 millimeter pressure sensors, and they sample at 50 hertz or something, 20 to 50 hertz. So we're getting 20 to 50 samples a second, but I don't know how the diaphragm properties change in very cold temperature. Mind you, the sensor measures the temperature and supposedly calibrates it out, but I don't believe it until I've done it in the lab myself. So I think they're really interesting implications. And you know this, when you go to the beach and it's January and you walk on the beach, you'll notice that it feels a little more solid, right? And so the question is, do we have to develop a different, what we call incipient motion threshold for frozen beaches? Does that give you a little bit of an idea? Thanks. Carrie?
Hi, thanks. I was wondering, of course, as an ecologist, more about the plant interactions, and I'm wondering about, from the perspective of sediment retention, I guess I thought I understood that, and maybe in Greg's model, that root elevation mattered, and I wondered whether plant detritus or like how much depth, I don't know if that interacts with sediment or changes with warming temperatures, or could you speculate about that?
I can only speculate, and it will be somewhat dangerous speculation. So as I understand it, one of the questions Greg asked is how much sediment can you actually get without negatively impacting the root structure? And he thinks that you can get up to 10 centimeters of sediment without impacting the root structure. I think the plant detritus gets really interesting because that also then, to a certain extent, can also impact the hydraulic resistance that Tracy Mandel does. So how resistant to the flow it is, which is going to control how much inundation and flooding you're going to get from the seaward side. But Greg Moore will be here later in the summer, so I suggest you corner him and ask him.
I have a question regarding the estuary project.
Yes.
For the inputted sediments, where did you source the materials that you then allowed the waste to deposit? And kind of a follow-up question to that, was the composition of the estuary, like inputted sediments, composed of what you had already found, or are we trying to compensate for sediment that had previously been lost because of the extreme weather conditions?
Yeah,
or
that's
events?
that's a great question. I'm going to start with a basic on beach nourishment projects and beaches. One thing we know about beaches is that the coarser the grain, the bigger the grain, the steeper they are. You see that here locally. When you have a really cobbled beach, it ends up being really steep. That is a function of the angle of repose of the beach. So one of the risks is that if you nourish a beach with coarse grains, over time, your beach may actually get steeper. This is potentially becoming an issue in Florida, places like Daytona Beach, where they have big flat beaches. If you actually nourish a beach with finer sediment, you'll end up with a flatter beach, which will then create more flooding and inundation on the seaward side. So you do have to find that sweet spot. What the Dutch proposed and what we're exploring, we're not proposing to do. I want to be really clear. We're not generating a mud motor here. But they actually used the sediment that was in the inlet that actually comes from the inland water. So it gets transported out with the outgoing tide from the tributary. So they're using the actual sediment that was actually in the estuary. And their thought is rather than scooping that up and taking it offshore and dumping it, maybe what they could do is sort of mix it up and it comes in and it can flood and it can settle out. That gets tricky because mud, does anybody here live in the Midwest? After a rain event, what color are your rivers? Brown. Anybody here live in Colorado? After a rain event, what color are your rivers? Nah, but they don't stay brown as long, right? Yeah. You end up, so one of the things we know is that once again, remember, bigger the grains, the steeper the topography, right? There's a correlation there that mud can actually stay suspended for quite a while. So you would have to then do a study to essentially say what size grain, and are we actually really going to dredge sediment in an inlet and then sieve it and say, okay, this is your 0.1 millimeter that you've spec'd? Probably not, but it's a question we at least have to ask because it does have important implications.
You talked earlier about that 70% of the people living in that community live on that coastal margin there. And I know a couple of friends who live there. And with all this data that you have and all this information that you have, how are you bringing that back to the cities well, not cities there, the towns there, and working with the unique town setups that we have in New Hampshire?
Yeah, it is, I just did a National Science Foundation field site and I learned a new term called polycentric. When you have all of these different jurisdictions that are all making decisions. Probably the hardest problem here is the social science problem. We do work closely with what's called SHAE, the Seabrook-Hampton Estuarine Alliance. So David Burdick, Greg Moore, to a certain extent, Tom Littman, work really closely with those folks so they can at least sort of learn a little bit more. And we also learn some of their problems, right? Turns out that one of the things in Hampton Seabrook Estuary that happens is that they think that if the tide level is going to be greater than 10 feet, then they know they have to evacuate. They know everybody has to move their car, but that's function of the winds. And remember that photo I showed at the very beginning, the movie I showed when there's offshore wind, you end up with different amounts of flooding in the estuary based on which way the wind is blowing. So one of the things that scientists, folks like myself, or more likely Tom Littman, can do is actually go back and actually help refine that. If it's 10 feet and the winds are blowing from this direction, then you need to evacuate. But maybe if it's 9 feet and the winds are blowing from this direction, you have to evacuate, or inverse. So I think that's one of the things that we're learning that we may be able to do. Greg and David Burdick also work a lot with restoring the marsh so that we can actually build the resiliency and the health of the marsh plants and ecosystem. Okay.
I was just wondering how the species that live in the salt marshes are affected by the the ice rafting and
Yeah,
the
it's a good,
additional sediment?
Natalie, that's a great question. So, what Greg has found is that I think in his preliminary study, and once again, this is why we talk about thin layer deposition. If we dump a dump truck of stuff, that's going to kill things, plants, animals, species, right? But if we're doing this in regular sort of influx of sediment and a very thin layer, then we have not identified negative impact on the species that live there. That doesn't mean that it couldn't happen. And you could imagine there could be a particular nesting season of a particular species where it may impact it, which is once again why the scientists almost have the easy job and the decision makers really have the hard job.
So online, Betsy writes, at Popham Beach in Maine, I think there was an effort to use people's Christmas trees to help rebuild the dunes last winter. I thought the store might have done in their efforts, but maybe not based on some of the things you have said. Any comments?
Yeah, so the idea is that you take people's old Christmas trees and you put them on top of dunes and you basically can, well, maybe you can trap sediment. Now, this assumes that you don't want the sediment going where the sediment was going to go, right? Maybe you don't put the Christmas trees in front of the salt marshes, but you do put the Christmas trees in front of the roads. So I think that could be a viable strategy. One point we even talked about, well, could you strategically plow in a particular direction to protect a vulnerable intersection, right? An intersection that's really important for evacuation. Maybe you can actually dump snow in a particular place. That though gets complicated because we use salt on our roads and we don't want to negatively impact the plant species with the salt.
Do we have any other questions in the room?
You mentioned a nuclear power plant earlier. I was just curious if is that under threat mainly of what's it called? Damn it. No,
Flooding and inundation.
yeah, flooding and inundation. Do you think restoring the local salt marshes kind of take that plant out of risk?
Restoring the local salt marshes will help protect any structure that is onshore of them. So I feel like, when I did a postdoc at Dalhousie and it was in oceanography and I was in the physical oceanography and our t-shirt said, it's not just oceanography, it's not just about the whales. I'm not saying whales aren't important. Let me be really clear. You're not recording that part, right? But I think that you could say a similar thing, right? To the idea that that we have to think about things from sort of this complex perspective. So sort of, I guess, is my answer to you. Yeah.
I think that wraps things up. We have time for one more question if someone has it. Otherwise, I just want to say, Diane, you could certainly do some of these same things here because I'm really interested in where the rocks are moving on when we get overwashed and it breaks Appledore into two halves.
It would be a
And
great project.
I think, I'm just saying, that would be
Yeah.
a really, really great project to
It
be
would
happening.
It would be a really great project.
I'd like to thank Diane for giving this lecture, allowing us to choose our own adventure as we go through and hear the things that she's been working on. And I want to thank all of you for coming tonight and joining us for the Rock Talk. For those of you online, feel free to join us next week. We have 8 o'clock Tuesday. We'll be having Rock Talk number 6. Thank you very much.
Thank you.